Good day everyone, we are group 7 and our topic is all about statistical independence. According to my research, statistical independent is two events are independent if the occurrence of one event does not affect the chances of the occurrence of the other event. The mathematical formulation of independence of the event A and B is the probability of the occurrence of both A and B being equal to the product of the probabilities of A and B. Statistical independent if f x given y does not depend on y, as is the case for example 3.20, then f of x given y is equals to g of x, and f x and y is equals to g of x times h of y. The proof follows by substituting f of x and y is equals to f of x given y times h of y into the marginal distribution of x, that is, g of x is equals to integral of negative infinity to positive infinite f of x and y dy is equals to integral to from negative infinite to positive infinite f of x given y times h of y dy. If f is given y does not depend on y, we may write g of x is f of x given y integral from negative infinity to positive infinity h of y dy. Now, integral of h of y dy from negative e to positive infinity is equals to 1. Since h of y is the probability density function of y, therefore g of x is equals to f of x given y, and then f of x and y is equals to g of x times h of y. It should make sense to the reader if x given y does not depend on y. Then of course, the outcome of the random variable y has no impact on the outcomes of the random variable x. In other words, we say that x and y are independent random variable. We now offer the following formal definition of statistical independence to the next reporter.
Okay class, the definition of statistical independence, definition 3.12, let x and y be two random variable, discrete or continuous, with joint probability distribution if x and y marginal distribution gx and hy respectively. The random variable x and y said to be statistically independent if and only if, and if x and y equal to gx and hy. So far, for all xy within the range.
The continuous random variable of example 3.20 are statistical independent since the product of two marginal distribution give the joint density function. That is obviously not the case, however, for the continuous variable of example 0.19, checking for a statistical independence of discrete random variable requires more thorough investigation, since it is possible to have the product of marginal distribution equal to the joint probability distribution for some, but not all combination of x and y. If you can find any point x and y for which f of x and y is defined such as that f of x and y is equals to g of x times h of y, the discrete variable of x and y are not statistically independent.
And now let's proceed to the example 3.2. So in example 3.21, show that the random variables of example 3.14 are not statistically independent. So we are going to prove. Let us consider that the points 0 and 1 from table 3.1 we find the three probabilities. The first is we find that the probabilities of f of 0 and 1 is equals of 3 over 14. The next is g of 0. The g of 0 is equals of the summations of f of 0 and y from 0 to 2 is equals of 3 over 28 plus 3 over 14 plus 1 over 28. So we come up the answer is 5 over 14. And also the h of 1 is equals of the summations of f of x and 1 from 0 to 2 is equals of 3 over 14 plus 3 over 14 plus 0 is equals of 3 over 7. So that f of 0 and 1 is not equal of g of 0 and h of 1. So therefore, x and y are not statistically independent. So all the preceding definitions concerning the two random variables can be generalized as to the case of nth random variables. So let f of x sub 1 and x sub 2 going to x sub n be the joint probability functions of the random variables of x sub 1 and x sub 2. So the marginal distributions of x sub 1, for example, is g of x sub 1 is equals of the summations of from x sub 2 to the summations of f of x sub 1 and x sub 2 going to n from x sub n.
For the discrete case, and g of x sub 1 is equals to integral of from negative infinity to positive infinity is to integral from negative infinity to positive infinity is f of x sub 1, x sub 2 to x sub n, dx sub 2, dx sub 3 into dx sub n. For the continuous case, we can now obtain joint marginal distributions such as g of x sub 1, x sub 2, where g of x sub 1, x sub 2 is equals to summation of x sub 1 into summation of x sub 2. This is a discrete case. For the continuous case, integral from negative infinity to positive infinity and to integral from negative infinity to positive infinity is f of x sub 1, x sub 2 into x sub n times dx sub 3 times dx sub 4 into dx sub n. We could consider numerous conditional distribution, for example, the joint conditional distribution of x sub 1, x sub 2, and x sub 3, given that x sub 2 is equals to x sub 4, x sub 5 is equals to x sub 5, and to x sub 2 is equals to x sub n is to retain. Note that big letter x is random variable and small letter x is the numbers of all random variable. F of x sub 1, x sub 2, x sub 3, given x sub 4, x sub 5 to x sub n is equals to f of x sub 1, x sub 2 to x sub n over g of x sub 4, x sub 5 to x sub n, where g of x sub 4, x sub 5 to x sub n is the joint marginal distribution of the random variable x sub 4, x sub 5 into x sub n. A generalization of definition 3.12 leads to the following definition for the mutual statistical independence of the variable x sub 1, x sub 2 into x sub n.
Definition 3.13. Let x sub 1, x sub 2 up to x sub n be n random variables of discrete or continuous with joint probability distribution f of x sub 1, x sub 2 up to x sub n, and marginal distribution f sub 1 times x sub 1, f sub 2 times x sub 2 up to f sub n times x sub n, respectively. The random variables x sub 1, x sub 2 up to x sub n are said to be mutually statistical independent if and only if f of x sub 1, x sub 2 up to x sub n equals to f sub 1 times x sub 1, f sub 2 times x sub 2 up to f sub n times x sub n for all x sub 1, x sub 2 up to x sub n with their range.
Example 3.22. Suppose that the shelf life in years of a certain perishable food products package in cardboard containers is a random variable whose probability density function is given by f of x is equal to e negative infinity x is greater than 0 and 0 elsewhere. Let x sub 1, x sub 2, and x sub 3 represent the shelf lives for 3 of these containers selected independently and find p x sub 1 is less than 2, x sub 2 is greater than 1 and less than 3, x sub 3 is greater than 2. So for the solution, since the container were selected independently, we can assume that the random variable x sub 1, x sub 2, and x sub 3 are statistically independent, having the joint probability density f x sub 1, x sub 2, x sub 3 is equal to f x sub 1, f x sub 2, f x sub 3, and is equal to e negative x sub 1, e negative x sub 2, e negative x sub 3. And since they have the same constant e, so it is equal to e negative x sub 1, x sub 2, and x sub 3. For x sub 1 is equal to 0, x sub 2 is equal to 0, x sub 3 is equal to 0, and f x sub 1, x sub 2, x sub 3 is equal to 0 elsewhere. Hence, gagamitin natin yung hinahanap sa problem, which is p x sub 1 is less than 2, x sub 2 is greater than 1 and less than 3, x sub 3 is greater than 2, is equal to integral from 2 to infinity, integral from 1 to 3, integral from 0 to 2, e negative x sub 1, negative x sub 2, negative x sub 3, dx sub 1, dx sub 2, dx sub 3. So this time for this problem, we will use the triple integral, and the result will be 1 minus e to the power of negative 2 times e to the power of negative 1 minus e to the power of negative 3 times e to the power of negative 2. And the final answer will be 0.0372.
And that would be all. Thank you for watching our video reporting. God bless and Merry Christmas.